Welcome. This is the second of two 30-minute sessions that will help you plan to teach the new Pearson EdXL GCSE Computer Science. In the previous session, we looked at the subject content of the new specification and how it is assessed. In this session, we'll be focusing on planning the course, considering some approaches to teaching programming, and providing an overview of the support available to help you. There are a number of considerations to take into account when planning how to teach the course. Like all other GCSEs, computer science is designed to be taught in 120 to 140 hours over 2 years in Key Stage 4. This works out at around 2 hours a week. Whilst centres may integrate key content into their Key Stage 3 programme, the 120 hours allocated to the course means that we strongly advise against trying to fit provision into less than the recommended number of hours, because it will prevent students from acquiring the skills, knowledge and experiences they need. The subject content of the GCSE assumes that students have followed the computing programme of study in Key Stage 3. Obviously, if this is not the case, then they will have a steeper than intended learning curve, which you will need to be aware of when planning the course. As a linear GCSE, students sit both exams at the end of their course. This has implications for teaching the theory in particular. An iterative approach in which topics are revisited and knowledge is deepened on each iteration is the best way of preventing students from having forgotten what they learned at the start of the course by the time they come to sit the exams at the end. There is a practical and a theory element to the GCSE. Principles and concepts assessed in paper 1, and problem solving with programming assessed in paper 2. The two papers are equally weighted, which means that the same amount of curriculum time should be allocated to each, 60 hours. Topic 1 covers the knowledge and understanding of problem solving and programming, and Topic 6, their practical application. For the purpose of planning, they should be considered as one unit of work and taught alongside each other. Learning to program is sequential and cumulative. Incremental reinforcement is key to developing students' ability to write code. A structured sequence of scaffolded programming tasks will provide the ongoing hands-on practice that students need. It may be stating the obvious, but worth saying nevertheless, your scheme of work must cover all the subject content of the GCSE and the specification. The Getting Started Guide and the Programming Language Subset, PLS, both provide additional information about the depth and breadth of coverage required. It is worth identifying any dependencies that impact on the order in which content must be taught. It makes sense, for example, to introduce students to binary patterns and units of measurement before teaching them how bitmap images and how sounds are represented in binary. Students won't be able to write conditional statements for loops unless they've already been taught about arithmetic, relational, and logical operators. It is a useful thing to do to lay out a teaching timetable for the whole course, planning backwards from the final exams in Year 11 or for your 2-year delivery. This will ensure that you allocate sufficient time to cover all the subject content without having to encroach on time set aside for revision. In the last session, I mentioned that we'd prune the subject content to ensure that students acquire a sound understanding of the fundamental principles of computer science. Nevertheless, there's a wide breadth of content to get through in 120 hours, and every lesson needs to count. It's not always necessarily important to write programs from scratch. Give students as much or as little keyboarding time as is needed to teach what you actually want them to learn, and avoid wasting time on typing. Don't try and teach programming in a single discrete block of time at some point during the course. Instead, have a continuous thread running throughout. With 2 lessons a week, one lesson could be programming related and the other lesson could be theoretical topics. Look to identify opportunities to link theory with practical work wherever you can. Consider using a spiral approach to teach programming. Introduce a concept and then revisit it at regular intervals, with each successive encounter building on the previous one, so that students expand their knowledge and improve their skill level. Bear in mind that it isn't necessary to use computers in every lesson. Even tasks that at first seem like they need a computer may be best taught using paper and pencils or by role play. For example, you could get students to act out a bubble sort or a binary search algorithm. For ideas on computer-free lessons, CS Unplugged and CS4FN both have a range of resources for engaging students in active, unplugged tasks. Build in assessment opportunities at regular intervals to check that students have understood what you've taught them. Periodically revisit previously learned theory concepts to ensure that students don't forget what they have already learned. For example, by setting homework tasks that require past learning to be revisited, or by using mixed topic quizzes in lessons that require students to retrieve knowledge spanning the entire GCSE content. Set aside revision time in Year 11 to go over theory content and prepare students for the exam. Learning to program is more than just about typing in lines of code. By the time they sit the practical exam in Year 11, students will need to be confident in amending and writing code and proficient in using the IDE of their choice. This slide lists the kind of tasks students are likely to encounter in Paper 2. They will be expected to amend code that someone else has written in order to correct errors, rearrange the lines to make it work, improve its readability, add comments explaining how it works, and add extra functionality. They're likely to have to convert a flowchart or a written description of an algorithm into code. The last question in the paper will always be a problem for which they must design and write a program from scratch. At the start of the paper, they will be given explicit instructions. For example, fix the syntax error on line 13, change the identifier X to a more meaningful name, or import the random library. By the end of the paper, they will have to decide for themselves what to do and how to do it, and write a program to meet these requirements. All of this has implications for how they learn to program and what they need to be taught. Python is a fully fledged programming language used by professional programmers to write complex software. Clearly, GCSE students can't be expected to master all of it in just 60 hours. This is a GCSE in computer science, not just in Python. In the last session, I mentioned the PLS, the Programming Language Subset. This is one of the 2 documents you should have to hand when planning the programming strand of your course. It specifies which Python programming constructs and library modules students need to know. All the tasks set in Paper 2 can be solved with only functionalities presented in the PLS. Students should practice solving problems using this restricted set. We're not expecting them to know the contents of the PLS off by heart. They'll have access to a hard and digital copy in the exam. Students will not be penalised if they use Python constructs not listed in the PLS. Its purpose is to clarify which parts of Python you have to teach and which ones you don't. The PLS specifies the what, not the why. That's the function of the Good Programming Practice Guide, which accompanies it. This explains the purpose of the constructs listed in the PLS and provides examples of their use. But there's more to programming than simply having a grasp of the basic constructs of a language. Students also need to master the procedural skills required to combine them in programs and solve problems. There's no denying that this is the aspect of programming that students find most daunting and that students have told us they find the most challenging to teach. But this also offers a great opportunity to differentiate students. PRIM, developed by Dr. Sue Sentence and the computing education team at King's College London, is an approach to teaching programming that is rapidly gaining ground. It is based on the premise that starting with existing code and being able to explain what it does gives students the confidence to write their own programs. PRIM stands for Predict, Run, Investigate, Modify, Make. Students are presented with a series of carefully scaffolded and targeted tasks that help them understand key programming concepts. Predict gives students the code for a program and asks them to predict what it will do. Run. Get them to test their prediction by running the program. Investigate. Get them to explore how the code works. Modify. Get them to edit the program, to remix code to produce a different outcome or to extend the scope of a problem. Make. Get them to make a new program that uses the same logic as the one they were given, but solves a new problem. The collaborative approach taken in PRIM is valued by teachers, as is the potential for differentiation. PRIM is just one of many tools in a teacher's toolkit. Some of the others that are useful to teaching programming are listed here. Debugging, which is giving students a program and letting them find and correct errors in the code. Parsons problems, giving students a program with the lines of code jumbled up and getting them to rearrange them so the program works. Faded, worked examples. Provided lots of scaffolding and providing lots of scaffolding at the outset to prevent students suffering from cognitive overload and becoming frustrated. As they become more expert with a concept, fade support so they have to solve more and more steps with a problem unaided. Reverse engineering. Give students a problem or a program and ask them to represent it as a flowchart or a written description. Unplugged activities away from the computer to support students' understanding of key concepts without them being distracted by trying to get their programs to work. Computers are precise machines. If you don't provide the necessary commands exactly as a computer expects, then the program won't work. Professional programmers are believed to spend more than 50% of their time locating and fixing mistakes in their programs. Because of this, expect students to get frustrated and need help and reassurance. You can't help them all the time, but this slide lists some strategies that are useful to try. Pair programming is more than simply asking two students to work together. One takes on the role of the driver, controlling the keyboard and writing the code. The other is the navigator, giving instructions to the driver, spotting errors, etc. Students swap roles at regular intervals. Peer-to-peer learning is a staged approach consisting of pre-instruction followed by multiple choice questions, and then peer discussion. It's been shown to help students learn, retain, and discuss programming concepts. Live coding is process-focused. The teacher develops the solution to a problem in front of the class so that students can follow the process. It helps learners understand the process of debugging and exposes them to good programming practices. Spot, where teachers work with students and where students can only seek help from teachers once they have exhausted all of their sources of support. First from their self, peers, others, and finally their teacher. Learning pit. You may want to introduce your students to the learning pit concept to reassure them that making mistakes and having to go back to the drawing board is part of the learning process and will help them develop their abilities and deepen their understanding. We're committed to supporting you to deliver great computer science teaching. This slide summarizes the extensive package of free support we've put together to help you. We talked about the Getting Started guide in the previous session. It provides useful additional guidance to help you understand what students have to understand and be able to do. There will be 3 sets of specimen papers. The first set will be available in September 2020, and the remaining 2 sets will be released during the course of the first academic year. They will provide additional exemplification of the assessment requirements, and in the absence of past papers, will be useful for setting internal mock exams. We will also have marked exemplar student work with examiner commentaries, which will illustrate the standard of work expected of students. You can use these with students as exam preparation. The first online event is the part of 3 pre-recorded getting ready to teach events. The other two events look in detail at the requirements of the two papers. I'm going to be talking about the editable scheme of work and the additional programme activities in more detail shortly, so I won't say any more about it right now. All Pearson standard support will, of course, also be available. Exam Wizard is a useful exam preparation tool containing of a bank of past questions, mark schemes, and examiners' reports. You can use these to create mock papers, homework, or practice tests in minutes. Obviously, the specification has changed, so not all the questions in the bank will be relevant, and of course, there won't be any yet for paper 2. Our Online Results Plus service provides detailed analysis of students' exam performance, helping you identify topics and skills where students would benefit from further learning to gain a deeper understanding of computer science. Our Subject Advisor service, led by Tim Brady, is a direct and personal source of help and support. We're in the process of writing a brand new scheme of work, tailor-made for the 2020 specification. This slide shows an extract from the top-level plan. We've divided the course into 120 one-hour lessons, grouped into 10 blocks of 12. As you can see, each block consists of 2 parallel strands. 6 lessons are allocated to computational thinking, and the remaining 6 to principles of computer science, mirroring the 50-50 split of the specification. The last lesson of each strand in each block is an assessment to check how much students have understood. For the scheme of work, if you drill down into any of the lessons, you'll find a detailed lesson plan and a PowerPoint presentation, plus lesson activities and a homework task with solutions. The lesson plan lists the spec statements covered and any resources that are needed. This lesson is from the computational thinking strand of the first block. It introduces students to flowcharts as a way of expressing algorithms. The animated PowerPoint presentation is used to teach students the meaning of each of the flowchart symbols, and a worked example is used to illustrate how they are combined in an algorithm. A Craig and Dave YouTube video is used to help explain how to produce algorithms. There are 2 classroom activities. One requires students to put the pieces of a flowchart in the correct order, and the other to develop an algorithm as a flowchart and then convert it into Python code. The 3 homework tasks provide additional reinforcement. Each block has 2 end-of-block assessments, one for each strand. They consist of a set of exam-style questions. The purpose of these assessments is to monitor students' learning and identify any aspects that need further work. The scheme of work materials will be published in batches. The first term will be available from the 12th of June. The materials for Year 10 spring and summer term will follow in July and August respectively. The materials for all of the Year 11 course will then become available in October, ensuring you will have everything you need and maximising your time for long-term planning. You can download the materials from the Pearson EdXL Computer Science 2020 page, Course Materials, Teaching and Learning Materials. We realise that every school and every class is unique. We know, for example, that some schools will include content from the GCSE in their Key Stage 3 programme of study. All materials are adaptable, with some suitable to work on a 2-week cycle, and many with options to vary their length. It's not our intention to impose a one-size-fits-all approach, but provide a solid foundation that all teachers can use to adapt to their centre needs. You can use the materials as given, customise them as much or as little as you want, or feel free to devise your own alternatives and share among the teaching community. We hope our offer will save you some time and effort. One way of using the scheme of work is to download it from the Pearson EdXL website as a set of zipped folders and install it to a local drive. Alternatively, you can access an online interactive version, which is designed to save you even more time and effort. In addition to the lesson plans, activities and solutions I've already talked about, the interactive scheme of work includes additional materials to support teaching Python and links to high-quality resources from leading providers, including NCCE's Resource Repository, Microsoft's Make Code, Craig and Dave's YouTube videos, and paulong.net, among others. I'll give you a whistle-stop tour of its key features. To create a bespoke scheme of work for your school, first give your scheme a name. Next, select Computing, then the course you want to deliver, GCSE Computer Science. You've then got the choice to select the length of your course as either 2 or 3 years. You'd then click Next. That would generate a recommended scheme of work organised to fit the teaching period you've specified. It will suggest how long you should spend on each unit and highlight any prerequisite knowledge that is needed. That's your starting point. You can then customise the scheme of work to how you want to teach and support your level of specialism. You can follow the suggested plan, adjust the timings, and drag and drop units to rearrange the ordering. Prerequisite knowledge is flagged so that you can clearly see any potential issues with the teaching order you create. Once you're happy with the scheme of work, you can click Save, and now share it with your colleagues and start using it to support your teaching. The Scheme Explorer, which is on the left-hand side, enables you to navigate your scheme of work easily. You can go directly to specific blocks or strands and allocate blocks to colleagues. Clicking on a block will give you all the relevant information you need, as well as links to the lesson plans, PowerPoint slides, activities, etc. The interactive scheme of work is free to access from the Pearson Edexcel website. You just need to register using your email address. You've told us that you need more practice material to help your students prepare for Paper 2. So we're developing a set of additional exercises, similar to the last question on the paper. Each one will consist of a question, a finished solution, and a commentary, and will be published early into the academic year. It's not necessary to purchase a textbook in order to successfully deliver this course. However, we know many of you like to do so. Our Pearson GCSE Computer Science student book has been given a radical makeover. Material that no longer needs to be taught has been removed, and additional content has been added to ensure that it provides all the content, activities, and exam support that you need to deliver the specification. The first half of the book is devoted to topics 1 and 6 and has lots of worked examples and practical programming activities, including some that follow the PRIM pedagogy. Key terms are highlighted and defined each time they occur in the text. Real-world examples and case studies of computer science in action appear throughout the book, helping to make the content more relevant and inspiring to students. There's a set of exam-style questions at the end of each section that use the Edexcel command words. They can be used to check understanding and/or for exam preparation. Then, preparing for the exam chapter is a section which is full of helpful exam tips for students. The student book has been written to work seamlessly with the scheme of work, but neither is dependent on the other. You don't have to purchase any resources, including those from Pearson, to successfully deliver this qualification. A new revision guide and workbook will be published early into 2021. Here are the contact details for Pearson Subject Advisor Service, led by Tim Brady. If you have any further questions about GCSE Computer Science, the team will be able to help you. Some further sources of help are shown here. On this slide lists some possible next steps you should consider taking. Sign up to Tim's monthly updates. Join the Pearson Computer Science community. Follow us on Twitter at Pearson_CS. Collaborate with colleagues on the Pearson Edexcel GCSE Computer Science Facebook group. And watch the next session in this series. Thanks very much.